welcome back. Today we're going to begin our exploration of a very important analytical tool known as infinite series, which is going to build into other analytical tools known as power series for functions and relations. So the first thing that I want to do before we jump into infinite series is just make sure that we understand what a finite series is first. So what is a finite series? And what makes it so different from an infinite series? So a finite series is one such as 1 plus 2 plus 3 plus 4 all the way up to some natural number, let's say m. So this is an example of a finite series because it is a collection of a finite number of terms. In particular, it terminates at some finite value. We can of course write this in summation notation as the sum from some index variable, say k, is equal to, and we start from 1 and we end at n, and we increment by 1 each time, and the variable that we're incrementing is k. So that would be a finite series, where that number there is a finite quantity. So in this particular scenario, we actually know what this finite series is equal to, and it's actually equal to n times n plus 1 divided by 2, right? It's a very famous arithmetic series. So what would an infinite series look like compared to this? So an infinite series would not terminate, so it would look something like 1 plus 2 plus 3 plus 4 all the way up to n, and would continue infinitely many terms after that. So we would write this as the sum from k is equal to 1 to infinity, i.e. we will sum forever and ever and ever, and so we're indexing with that variable k. So if we were to define this in terms of a finite series, the practical only difference in these notations is that this is now an infinite quantity or an infinite idea. Moreover, if you had not defined infinity as a quasi-infinite number or something like that. So what we have here is in some sense a limit as n goes to infinity of that finite series, the sum from k is equal to m of k. So if that is the particular case, then that means this is precisely equal to, for this particular example, the limit as n goes to infinity of n times n plus 1 divided by 2. Right? So this infinite series is just the limit of the finite series associated to that, which is sometimes referred to as the partial sum of the infinite series, because we're just taking a finite portion of that infinite series, right? And this gives us a good way of defining exactly what an infinite series is. Okay, so definition. So if the limit of the partial sum of this summation, the sum from k is equal to infinity, of some sequence ak exists and let's say it's equal to some number L. And let's of course mandate that it's not equal to plus or minus infinity in the case you have defined what that even means. Then we say that the infinite series converges to this number L, and if it doesn't converge, we say the infinite series diverges. And some people will say it diverges to plus or minus infinity, 1, or both of those, right? So that's what an infinite series is and what it means for it to converge or diverge. Now, I just need to make one thing clear. So the sum from k is equal to infinity of some sequence ak is equal to the limit as n goes to infinity of the partial sum, the sum from k is equal to n of AK. It's not the same thing as the limit as k goes to infinity of the partial sum. They are very, very different ideas. Right? So that's the basic idea associated to infinite series. So what we can do is we can see if we can generate a particular infinite series. But we already have one, in particular the sum from k is equal to infinity of k. Does this infinite series converge or diverge? Well, we know that this is just going to be equal to the limit, as n goes to infinity, of the sum from k is equal to n of k. We know that, at least from the definition of an infinite series. And that's going to be equal to the limit as n goes to infinity of n times n plus 1 divided by 2. We know that a quadratic function grows faster than a constant function, therefore this is equal to a positive infinite quantity, which means that this infinite series, the sum from k is equal to infinity of k, diverges. Right? So that's an example of a divergent series. Let's see if we can build a convergent series. So let's start off with a couple obvious things. And this derivation, I guess you could call it, it's also going to give us some foundations of things that we definitely should keep in mind or stay away from. So I'm pretty sure that everyone would agree that 1 is equal to 1, and most people would agree that I can subtract and add a quantity to the expression and not change its value because that's just equal to 0. I can also take away x squared and add x squared. I can take away x cubed, add x cubed. I can take away x4, add x4, and I can do this as many times as I want, and we are just adding 0 each time. So in some sense we have a 0 times infinity case here, but in this case this is precisely equal to 0. Because we're just taking the limit of 0, which is just equal to 0 as n goes to infinity. So we're safe, at least in that regard, assuming that this number x is sufficient. But we'll talk about what we mean by sufficient in just a moment. So let's look at this expression that I have here. And what I'm going to do is I'm going to factor by grouping. So I'm going to group these two terms together, those two terms, and those two terms. Notice that I can't really take anything out of 1 and x, so the greatest common factor would be 1. I can factor out an x here, an x squared there, an x cubed there, and so on. So that means 1 is the same as 1 times 1 minus x plus x times 1 minus x plus x squared times 1 minus x. We'll also have an x cubed in the next term, 1 minus x plus and so on. Notice that I have an 1 minus x in every single one of these terms, and hence I can factor it out. So I'm going to have 1 is equal to 1 minus x times 1 plus x squared plus x cubed plus x to the 4, and so on. So what I can do here is I can divide both sides by 1 minus x, provided that that is not equal to 0, which means that x cannot be equal to 1, so that's going to be at least one restriction on this expression. And then I have, at least on the right-hand side, which is now going to be my left, is an infinite series, right? So we have that 1 plus x squared plus x cubed, and so on, is equal to 1 over 1 minus x. So we have a number, because we're going to be assuming that x is a real number, except for 1, at least that's the only issue that we see here, is equal to an infinite series on the left-hand side. So we have that the sum from k is equal to, and keep in mind this is just x to the 0 and x to the 1, so this is the sum from k is equal to 0 to infinity of x to the k. This is equal to 1 over 1 minus x. Right? So we have this particular expression, and clearly x cannot be equal to 1. Right? But another question you can ask, is this the only issue? Right? So we have to test this infinite series to make sure that all values that we plug into this actually converge to this value, right? So this is an infinite series. X is just a number. 1 over 1 minus x is just a number. So our claim is that this infinite series converges to this number 1 over 1 minus x as long as x satisfies some requirements. So it's obviously not true for x is equal to 1, so let's try a couple other different values. So for example, let's try x is equal to 0. So that's going to be equal to 0 to the 0, plus 0 to the first, plus 0 to the second, plus 0 to the third, all the way out to, for example, 0 to the n, and that's going to be equal to, keep in mind that's going to continue onwards, and that's going to be equal to 1 over 1 minus 0, question mark. So what do we have here? So what is the partial sum of this particular expression? Well, 0 to the 0 is quite interesting, so I'm just going to leave that there just for a moment. So that's just going to be equal to 0 to the 0, whatever that is, plus all these things are just going to be equal to 0, plus all the way out, right? So this is the partial sum, and my claim is that that's going to be equal to 1 over 1 minus 0, right? So if it does converge, well, what is 0 to the power of 0? Well, that's technically undefined, and undefined plus 0 is still undefined, but the right-hand side is just equal to 1. So we have that 0 to the 0 power must be equal to 1 if we were to define it, right? But keep in mind 0 to the 0 cannot be absolutely defined, so we can define 0 to the 0 to be conditionally defined. Conditionally defined to be 1. And some people will just abbreviate that with C above that equal sign. So this is a conditional definition of 0 to the 0 power. Right? Because we know that with limits and indeterminate forms, 0 to the 0 can take many different expressions, right? So that's the conditional definition. And if you're willing to accept 0 to the power of 0 to be equal to 1, then x is equal to 0 does satisfy, right? But what about other values for this, right? So x equals 0 is a weird case, but it sort of works in some sense. Now let us consider the case where x is bigger than 1. For example, we consider 2 as a base case. So we're going to have 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus all the way down to 2 to the power of m plus and so on. That's going to be equal to, by this formula, 1 over 1 minus 2. And 1 over 1 minus 2, that's going to be equal to 1 over negative 1, which is equal to minus 1. So we see here on the left-hand side, this is just going to be equal to the sum of 2 to the power of something, which is all positive numbers. So all positive numbers, and it's also increasing, right? So if we look at that partial sum, for example, a to the m, which is equal to 1 plus 2 plus 4 plus 8 plus 16 plus all the way out to 2 to the m, if we look at that particular expression, that's going to be an always increasing sequence. Does it get closer to negative 1? It's impossible for that to be the case, right? So this does not make sense. So this is not true, at least under standard addition rules, since this is an always positive and always monotonically increasing sequence. So x cannot be greater than 1, right? So that's a really bad thing. Right. So let us also approach 1 from the right-hand side, right? So let's assume that x approaches 1 from the right-hand side. So x is still greater than 1, but arbitrarily close to 1 from the right-hand side. So for example, if epsilon is an infinitesimal, a positive infinitesimal, 1 plus epsilon would be a suitable case here. So when x is really close to 1 from the right-hand side, the sum from k is equal to 0 to infinity of 1 plus epsilon to the power of k is practically equal to, at least in the real part sense, approximately equal to the sum from k is equal to 0 to infinity of 1 to the power of k, which is just the sum from k is equal to 0 to infinity of 1, right? Which, at least the partial sum, is going to be the sum from n is equal to infinity of n, because 1 plus 1 plus 1 plus 1 n times is just equal to n, and we know that that's equal to positive infinity. So if we plug that in into our expression 1 over 1 minus 1, something really close to 1 but on the right-hand side, that's also equal to positive infinity. So in some sense, as long as you're willing to define positive infinity, this always also works as well. But notice that if we want to test all of these individual cases, it gets really, really case sensitive and sometimes very complicated and sometimes requires you to stretch your mind a little bit, which is sometimes not a good way to approach how to solve when do these series converge and stuff. So that's where a theorem such as this one is going to come in handy. So there's a theorem, and it says this. The sum from k is equal to 0 to infinity of ak, where ak is some sequence, converges if and only if the integral from 0 to infinity of fk dk converges. And when I say if and only if, that means if this converges, that means that converges. If this converges, that means this converges. And if one of them diverges, the other will also diverge as well. Some people will refer to this as the integral test for convergence. And the reason this is useful is because we actually already know how to test whether integrals converge or diverge, because we just, use the definition of improper integrals and see if it's a finite number or not. Right? So let us jump back into our previous example where we were interested in where or when does the sum from k is equal to 0 to infinity of x to the k, when does it converge in particular to this number 1 over 1 minus x? So what we can see is, okay, well, this is going to converge whenever the associated integral is going to converge as well. So the integral that we're going to be interested in is the integral from 0 to infinity, same limit bounds, of that particular expression, x to the k, and the variable here is k, not x. So x is just a number here. So this is similar, for example, to the integral of 5 to the x dx. So that's practically the type of function that we're looking at here. So we know that the integral of an exponential is just an exponential. We just need to divide by the natural log of 5 in that particular case, or the natural log of x in this particular case. So that's going to be equal to x to the power of k, all divided by the natural log of the absolute value of x. And then we need to take the limit as k goes to infinity and as k goes to 0. And notice here that the natural log of x cannot be equal to 0, which means that x cannot be equal to 1, which we've already stipulated in the previous analysis of this. So if x is not equal to 1, then we can actually factor that natural log of x out because that's just a constant. So that means our integral is equal to 1 over the natural log of the absolute value of x, and then times x to the power of k as k goes to infinity, and as k goes to 0, which we can look in limit form as 1 divided by the natural log of the absolute value of x times the limit as k goes to infinity of x to the k minus the limit as k goes to 0 of x to the k. Right? So, what is the issues with the limit as k goes to 0 of x to the k? Well, anything to the 0 power is equal to 0, provided that x is not equal to 0. But we can conditionally define 0 to the power of 0 to be equal to 1, so that's not an issue. We've already figured out the issues with that leading term, x is not equal to 1, that's not an issue. So the convergence of this particular integral is primarily dominated by this particular term, the limit as k goes to infinity of x to the power of k. So we actually already know when that particular expression converges or not, because, for example, if x belongs to the interval 1 to the infinity, then we're going to have, for example, the limit, as an example, as k goes to infinity, of 5 to the power of k. We know that's going to be equal to positive infinity, so that diverges, obviously, when x belongs to that interval. And when x belongs to the interval minus infinity to 1, then as an example, what do we have? So we're going to have the limit as x goes to infinity of negative 1 to the power of k and then 5 to the power of k, for example. And that's going to be oscillating between plus and minus infinity because it's sort of going to go up in an exponential fashion, both in the positive and negative spectrums, right? So that's obviously going to diverge, right? So x cannot belong to those particular intervals. So that only leaves the other cases. So for example, when x belongs to the interval 0 to 1, then we have, as an example, the limit as k goes to infinity of, say, 1/2 to the power of k. Well, that's just going to be equal to the limit as k goes to infinity of 1 over 2 to the power of k, and we know that constants don't overtake exponentials, so that obviously goes to 0, which means that that integral converges, which means it converges the associated series for 0 to 1. And also similarly, when x belongs to the interval -1 to 0, then we're going to have a similar effect, but instead of getting close to 0 from one side, it's going to sort of bounce between positive and negative things, but still it's going to go to 0. So that gives us our criteria for the convergence of that series. So that means the sum from k is equal to 0 to infinity of x to the power of k is equal to 1 over 1 minus x only if 0 is less than the absolute value of x is less than 1. And technically it will converge when x is equal to 0 if you conditionally define 0 to the power of 0 to be equal to 1. So we have this particular and very magical result, which is sometimes referred to as a geometric series. Right? So let's just look at a couple examples of numerical evaluations of this geometric series. So let's just look at a quick example. Does the following series converge? So the sum from k is equal to 0 to infinity of 1/2 to the power of k. So this is obviously a geometric series where that's our x value, and we know that 1/2 belongs to the interval 0 to 1, and hence this series converges. But what does this series converge to? Well, since that number is between -1 and 1, it's going to converge to 1 over 1 minus that value, which is 1 over 1 minus 1/2. So if we look at these values, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, they're getting bigger, but they're not really growing faster as n gets really big. In particular, the sum is going to get closer and closer to 1 over 1 minus 1/2, which is equal to just 2. Right? So if we look at another example, for example, the sum from k is equal to 0 to infinity of -1/3 to the power of k, which is just going to be 1 minus 1/3 plus 1/9 minus 1/27 plus 1 over 81 minus plus and so on. Again, this number is in between -1 and 0, hence this geometric series converges. And it's going to converge to 1 over 1 minus 1/3, which is just going to be 1 over 1 plus 1/3, which is 1 over 4/3, which we know is just going to be equal to 3/4. So if you add up a bunch of these terms in order, you're going to get a number that's close to 0.75. And also make sure that some people do change this boundary to like k is equal to 1 or k is equal to 2. In that case, you would just subtract off, for example, 1, add 1/3, subtract 1/9, if it decides to start at a particular value other than 0. Now that we've looked at a very common infinite series, known as a geometric series, and we've actually already analytically derived when that particular infinite series does converge, let's take a look at another infinite series that actually has quite a few applications as well, which of course we won't get into, but we'll talk about this series today. Some people call it a p-series, and some people also call it a zeta series. So this infinite series takes a similar look as the geometric series, but it looks at reciprocals instead of monomial terms. So this is going to be defined to be the sum. Now this one starts at 1, not 0, and again it goes to infinity, and it's defined as 1 divided by k to the power of p. Right? And when this converges, we're going to say it converges to zeta of p. Right? So this, when you expand it, is going to look at, for example, 1 over 1 to the power of p, 1 over 2 to the power of p, 1 over 3 to the power of p, 1 over 4 to the power of p, plus 1 over 5 to the power of p, plus all the way out to 1 over n to the power of p, and so on. So one can ask, well, for what values of p does this infinite series converge? And when it does converge, we're going to say it converges to zeta p, right? So we need to answer the question, for what p does this expression, zeta p, exist? All right. So we can use the integral test again to test the convergence for this particular series, because we know that this series is converge whenever the associated integral from 1 to infinity of 1 over x to the power of p, which is the same as x to the minus p dx, converges. Right? So when does this particular integral converge? So by using the power rule, that's going to be equal to, so we're just going to add 1 to that exponent, and then we're going to divide by that new exponent, which is negative p plus 1, and I'm actually going to write this instead as x to the 1 minus p over 1 minus p, because it's actually a little bit more easier to evaluate. And then we're going to evaluate this as x goes to positive infinity and x goes to 1. Right? And we're going to see what values of p does this converge to. So obviously that 1 minus p on the bottom can't factor out since it's a constant. So we can write our integral as 1 over 1 minus p times x to the 1 minus p as x goes to infinity, as x goes to 1. Clearly we have an issue here, so p cannot be equal to 1. So that's the first restriction that we have. And you might be like, well, what's so wrong with p is equal to 1? So when p is equal to 1, we're going to have the integral from 1 to infinity of 1 over x to the 1 dx, which we know is going to be equal to the natural log function evaluated as x goes to infinity as x goes to 1, which is equal to the limit as x goes to infinity of the natural log of x minus the natural log of 1, which we know is equal to 0. And we know that the natural log function grows without bounds, so that integral diverges, and hence the associated p series also diverges, which means that zeta of 1 does not exist. Right? So that's what that first term gives us. Now let's take a closer look at that particular expression and see when that converges or diverges. So we have 1 over 1 minus p, and we already know what that gives us. And now let's take a look at the limit as x goes to infinity of x to the 1 minus p minus the limit as x goes to 1 of x to the 1 minus p. So here we're going to have 1 to the 1 minus p, and as long as p is not infinite, for example, 1 to the anything power is just going to be equal to 1, so that's not going to give us any issues. So if any issues does occur, it's going to be associated to this term right here. So let's take a closer look at what's going on with that particular limit. So let's break this up into particular cases. Keep in mind p cannot be equal to 1. So let's dance around 1 to analyze the convergence on the left and the right of 1. So first off, I'm going to consider the case when p is greater than 1. So when p is greater than 1, what can you tell me about the number 1 minus p? So if p is greater than 1, that means p is like 2, 3, 4, and 1 minus 2 is a negative number. 1 minus 3 is even more negative. So this is going to be a negative number. And when 1 minus p is negative, that means p minus 1 is a positive number. So that means what? So that means the limit as x goes to infinity of x to the 1 minus p. So 1 minus p is negative, so I can write that as the limit as x goes to infinity of 1 over x to the p minus 1, where p minus 1 is positive. So if that's a positive exponent, that means it's like x squared, x cubed, x4. So that grows without bound, and hence this is equal to 0, which means that that integral converges, which means the associated infinite series also converges for p is greater than 1. So that's a very good thing. If we consider the case where p is less than 1, that means 1 minus p is going to be bigger than 0, because p is like equal to a half, which 1 minus a half is a half. 1 minus 0, 1 minus negative 1, 1 minus negative 5 is positive 6. So those are all going to be positive numbers. That means when we take the limit as x goes to infinity of x to the 1 minus p. This term is like x squared, x cubed, which means it's going to grow without bound, and in particular go to positive infinity, which that is a bad thing, and hence that particular integral diverges, and hence the associated infinite series also diverges as well, right? So that means this infinite series, the sum from k is equal to infinity, 1 over k to the p converges to this special number, zeta p, as long as p is bigger than 1. So if we define this zeta value as a function, just like we do, for example, natural log of 2, we extend to, for example, a function called the natural log of x. So if we define, for example, this zeta function, some people also call it the Riemann-zeta function. Let's call it, for example, zeta x, which is defined to be equal to the sum from k is equal to infinity of 1 over k to the power of x. The domain of this particular function is going to be the interval 1 to infinity, because that's the same exact interval for which the associated infinite series converges. Now, does zeta 1.5, zeta 2, zeta 3, zeta 4, zeta 5.8 have specific values? Maybe, but keep in mind we already use notation to represent a more complex number. For example, zeta 7.8 is no more special than, for example, the square root of 5 or the natural log of 8, which we already use, maybe even the square root of e we don't have a symbol for. So these are perfectly standard representations. For example, the sine of pi over 17.3 might not have an analytical value, but that's okay. We can always represent it because that's what we're talking about. Now sometimes, for example, the natural log of 1 does have a beautiful value. For example, the sine of pi over 4 is equal to the square root of 2. That's a beautiful value. Some people do try to find analytical representations for some of these constants. For example, if we look at zeta 2, which is equal to the sum from k is equal to 1 to infinity of 1 over k squared, this actually does have a beautiful analytical value. It's actually equal to the pi squared over 6. I'm not going to prove that here, but generally speaking, that's a very beautiful answer. But if you don't know the analytical value of this, we know that this infinite series does exist because this value in the exponent is bigger than 1, hence that infinite series converges, and we can just say it converges to zeta 2 in the case you don't know what pi squared over 6 looks like. Because most of these series, for example, the sum from k is equal to 1 to infinity of 1 over k to the 8.7, this, at least as far as I know, does not have a beautiful value, but we do have a name for it that's just going to be zeta of 8.7, because 8.7 is bigger than 1, and that is perfectly okay. Now, if somebody says, okay, well, what's the sum from k is equal to 1 to infinity of 1 over k to the power of 0.7? 0.7 is not bigger than 1. I mean, you can say zeta of 0.7, but this does not exist. Therefore, you shouldn't be writing that expression, and since that series does not converge, that's okay. Now, I just want to make one very important thing clear, and it's the following statement. So just because a series converges doesn't always mean that we know exactly what it converges to. Now, this of course challenges some mathematicians and some people who like these kind of puzzles to try and find what those values are, but generally speaking, it can be very complex to find out the exact value of what it is. The last thing I want to do is consider a couple infinite series that are actually quite used in some analytical applications. One converges and one does not. So let's first off introduce the one that does not converge, and that's the sum from k is equal to 1 to infinity of 1 divided by k, or 1 divided by k to the power of 1. So we know that, at least by definition, would be equal to zeta 1, but 1 doesn't belong to the domain of the zeta function, and hence this expression does not exist because that series diverges, right? So that diverges. So if we consider another expression, and it actually looks very similar, let's throw an alternating sign in front of that, in particular negative 1 to the power of k plus 1 of 1 to the k, right? Does this converge? Well, even though we already have a name for this, this is just a p series with p is equal to 1 or zeta 1. Some people actually give this another name. This is called a harmonic series. And if you look at the partial sums, that's just 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. So the terms do get smaller, but they don't get small enough fast enough for it to converge compared to, say, 1 over n squared or something like that. So when we consider the alternating term, which is going to be equal to, so k is equal to 1, so 1 plus 1 is going to be equal to 2, which negative 1 to the 2 is equal to positive 1. That's going to be 1 minus 1/2 minus 1/3 plus 1/4, or whatever signs, 1 minus plus, minus, plus, minus, plus, minus, and so on. Does this converge? And if so, to what? Now keep in mind, you might not know any rules that stipulate whether this converges or diverges, because it's not a p-series, because it has that alternating term, right? So this is usually what we refer to as an alternating infinite series. But I'll state a nice little rule that actually guides how to know whether this converges or diverges. And keep in mind, even if we do know it converges, it doesn't necessarily mean we know what it converges to. But this one, we actually can perform some cute integral tricks in order to figure out exactly what it is. And I'll sort of walk you through that and show you some of the beautiful tricks that some people use to prove the value of convergence. So let's consider this series from 1 to infinity of negative 1 to the k plus 1 of 1 over k, and let's look at the expanded representation. So 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus minus, and so on. So one can show that 1 can be equivalently represented as the integral from 0 to 1 of 1 with respect to x. We can represent 1/2 as the negative integral from 0 to 1 of x dx, because x integrates to x squared over 2, and that over 2 is that 1/2 because x squared just goes to 1. And then we're going to have plus the integral from 0 to 1 of x squared dx minus the integral from 0 to 1 of x cubed dx plus minus, and so on. So we just have a bunch of integrals that sort of came out of nowhere with this. And I think this approach is actually quite elegant. So since integrals are linear operators, we can factor out that integral. So we have the integral from 0 to 1 of 1 minus x plus x squared minus x cubed plus x4 minus x5 plus minus, and so on. And we're integrating with respect to x, and we have this expression. So what I want to do now is I want to factor out 1 out of those two terms, x squared out of those two terms, x to the 4th out of those two terms, and continue factoring by grouping. So once I do that, I'm going to have our integral from 0 to 1 of 1 times 1 minus x plus x squared times 1 minus x plus x4, 1 minus x. Next would come x6, 1 minus x plus all the way down to infinity dx. I have a 1 minus x here, so I can factor that out. So this is going to be equal to the integral from 0 to 1 of 1 minus x, and then we're going to have 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th all the way down to infinity dx. Right? So what do I have here? So that looks like an infinite series. So let's write that in infinite series form, and keep in mind that's just x to the power of 0. So I can write that as the integral from 0 to 1 of 1 minus x times the sum from k is equal to 0 to infinity of x squared to the power of k dx. Now keep in mind, x belongs to the interval 0 to 1, That means x squared also belongs to 0 and 1, which means that this series right here converges, because that's just a geometric series where that term that's being exponentiated is x squared compared to x, but x squared's in that interval of convergence, and therefore that converges. And what does it converge to? 1 over 1 minus that term. So that means that our infinite series converges to the integral from 0 to 1 of 1 minus x times 1 over 1 minus x squared dx. Now I can factor that difference of squares that we have there in the bottom. So we have that our infinite series converges to the integral from 0 to 1 of 1 minus x times 1 over 1 minus x, 1 plus x dx. And we see that these 1 minus x terms cancel, just leaving us with the integral from 0 to 1 of 1 over 1 plus x dx, which integrates very, very nicely. So our integral is going to be equal to the natural log of 1 plus x as x goes to 1 and as x goes to 0, and then we're going to subtract. So that's going to be equal to the natural log of 2 minus the natural log of 1. So minus the natural log of 1. And then the natural log of 1, that's just going to be equal to 0. So we're just left with the natural log of 2. So this series, the sum from k is equal to infinity, of negative 1 to the k plus 1 of 1 over k does converge, and in particular it converges to the natural log of 2. And the reason we know it converges to the natural log of 2 was because we transformed this into an integral that had a geometric series for which we've already stipulated the convergence of. So one can ask, well, if I have an arbitrary alternating infinite series, in particular one of the form the sum from k is equal to some finite number to infinity of negative 1 to the power of k of some sequence ak, when does this converge? So we can actually tell when an alternating series converge, and some people also call this the alternating series test. And the only thing we need to look at is this term ak. So the first requirement that must satisfy is that the limit as k goes to infinity of ak, this must be equal to 0. In particular, it's a decreasing sequence. Now, of course, if the limit is equal to 0, that doesn't imply that it's a decreasing sequence, so we have to mandate that ak is positive for all but finitely many terms. And when I say finitely many, for example, it can be negative or positive like that, but it eventually has to be always positive, right? And in particular, the limit has to be equal to 0 for that particular expression, right? So since the terms are going to be positive for all but finitely many, which means it's going to be positive for infinitely many, and the limit is equal to 0, that means it has to be eventually decreasing for that to hold. So if we have an eventually always positive decreasing sequence for that particular sequence ak, then we have evidence to believe that this alternating series will converge. So for example, if you have, as an example, the sum from k is equal to 0 to infinity of negative 1 to the power of k squared plus k plus 5 over k cubed plus k to the power of k, then obviously we have an always positive sequence, we have an always positive sequence, therefore this is an always positive sequence, and we know that tetrations will always dominate polynomials, so this term is going to go to 0 in the limit, and since that goes to 0, that's an always decreasing sequence, and by the alternating series test, we have that this sequence or infinite series does converge. But of course, just because it converges doesn't necessarily mean you know what it converges to, but you can always approximate what it converges to by choosing an arbitrarily large number and look at the partial sums for that particular infinite series. So those are all of the important things that you definitely should know when working with infinite series. There's several other little tricks and tests for convergence that we will discuss later, but we'll wait until a later time. I hope you enjoyed this video, and I'll see you in the next one. Take care.